use Parse RecDescent. Parse RecDescent is a model written by Damien Conway, and mainly its aim is to try to identify patterns of some sequential data using a grammar to obtain more complex data which is more suitable for processing. Some reason why this could be useful is, for example, to distinguish different kind of information which have the same information inside, but they are constructed with different forms. Interpreter IRC commands for bot, or try to realize how secretly linear words, identify set of rules, parameter language, is source code, or try to transform with text to HTML. So, more precisely, Parse RecDescent helps us to isolate the logic from the parsing, normalize different kind of data, try to understand the context and where the data is. But first, I would like to explain a bit more what a grammar is. Grammar is a set of rules where every rules have an alternation of production. A production may refer to other rules, terms, directives, or action. At the end of all this grammar, we have terminals, which are strings or just regular expressions. In this example, we have a very simple, useless grammar where we call it rule, which have two alternation, two production, foo barcodes and left, right. In this case, foo barcodes are reference to other rules. And this rule matches if the first production works, if it is failed, try the second. This is another example of another grammar of these words, still useless words, which we have a main rule called A, which requires to match B or C for given error. B try to consume capture foo and try C, and C try to capture bar. If we fed this grammar with bar, that would happen. A, which is invoked, try B, which fails because it's not able to find foo. Then go back to C, which match and return bar, and in this case, A match return bar. If we fed foo bar, well, pretty close, similar, but in this case, A will match B because we have foo, which match C, which match bar. If we fed other, that will not work because neither B or C are able to match, and so we get an error. I would like to show you exactly what is the error, which is very explanatory, and we have written no more than just error. Another thing may happen when we set foo back. The foo back, well, this grammar will fail, but it fail in a particular way because when A tries B and B is able to consume foo, C will fail, and so everything will fail. We're backing to A again, and this is called backtracking, like a regular expression. This is maybe a bit more useful example. We have a date, it's in a new format, and we want to try to identify and match these dates. So the date as a weekday, a month day, comma, month and year. Weekday is just a list of items in an affirmation. The date have three strict terms and then a regular expression. Month and year are pretty close to the same. This grammar match these dates. But if it happens that you may have two kind of format for this information, this or this, we may change this grammar, allowing another production for the date, which uses the year minus a number minus another number. With just few changes in this grammar, we are able to match those two things. Our suggestion is per mode. So, where is the per? Per is here. The grammar, and paradox, the same grammar above, and the parser, our suggestion, new grammar, and per is proof. So we move it. Pretty easy. What happened before we checked, I didn't tell you, is that when we fed this grammar with full bar, we really matched full and bar. But every time a production is matched, we could return the last term of the production. So in this case, with full bar, what we are getting back is just bar. It's blur. I'll try to explain it a bit more. A try B. B consume full and try C. C consume bar and return bar. At this point, B, having matched C, return exactly what C returned, so bar. And again for A. We may need to return more information because we have matched not only bar, but full bar. And so we can use actions. This is a parser RecDescent action, which is executed at the canonical time of this is matched. So when exactly C is matched and we succeed, this action is executed. Return the first item, which is full, and the second item, which is C, with an arrow inside. So that's exactly what we have got to return. The item starts from 0, and the 0 is the name of the rule. This is very useful later. Parser RecDescent helps us because every time we need to match something, we need to declare the action we're going to use. But there is the RD auto action, which automatically applies this action to every production that does not end with already mentioned. This action returns an hash reference where the name of the rule and as a value an array of items. So again, the same grammar, but using this new action for every rules, we will get exactly the parse tree, which explains clearly what happened inside our grammar. Another interesting thing with parse RecDescent as the comment. This is a part of a grammar where we may have a proc command. A proc command may be a kill of a pet or a list of process. Suppose that we are going to feed this grammar with kill full. Kill matched, but not the pet. Anyway, we know it is a kill, so there is no reason to try the other production. We already know we are in the right cases. If the bit is missing, this is an error. We do not want to backtrack in this case. The comment paired with the error with the question mark makes things more useful because we do not only backtrack in these cases, but generate an error if a production which was already commented fails, giving this error. Invalid per comment was expecting feedback from full Steve. So this little piece of grammar may exit in different situations. With a key tree, that's okay, we pass it. With a yes, again. With key foo, we will get an error, but with foo bar, we just return. Try order production. So we are going to keep errors exactly when we expect them, but we know this is an error situation. We got through two big gains, reduce the backtracking, and generate persist error when it happens. Okay, so we will try to make things more complex, try to generate a SQL grammar able to parse every SQL language. Supposed to be, because C# are a lot of dialects, slangs, and so on, to be corrected in a subset, which it works for other cases. But first, we need to consider the subrules. We already used this case when a rule refer to another. But when we refer to others, we may use multiplication of the matches. So in this case, I will match one or more times apart, or in this case, it's 0 or more times separated by commas. 0 or one time, and using and or like a separator case instead. What we want to do is try to parse something like that and get something like that. And this is the grammar we're going to use. We will try to identify some hotspot in this grammar and try to explain them a bit more. I added that this is a necessity, a trick that we need to do when we use parse RecDescent. Parse RecDescent consumes up to when it is able to. And if we are going to match an entire SQL statement, it may be ends just at a particular point when there is a syntax error. We want not to parse only up to that, but we want to parse everything or give an error. So these things force us to parse all the data in it. Oh, and another interesting thing that I forgot to mention is that when we use subrules, this as will get an array reference automatically. The statement we have defined was select meant some columns separated from a word and a order by. If this match, we are going to return a blessed array ref with the fields we net. So 3 is the columns, 4 is the from, 5 is the word, 6 is the order by, and blessed as a select object. It is quite obvious that a select object or another package may be getting a lot of benefit for changing this information or use them in some ways. In the select, there was a word condition. The word condition required obviously the word, followed by some conditions, or an empty things. I was not able to return on that because an action is part of the match. So if an action return on that, then it's like a failure. So this would be go back to the track. So I will return an empty action, which is true. But the laptop is a new directive we're going to use. Laptop means a condition followed by other condition with left associativity. Associativity as characteristic of every infix we're going to use for binary operators. Easy, understandable by this example. The addition, or in this case the subtraction, is left associative. It is required to be evaluated from left to right. So first we have to calculate 5 meaning 4, and then minus 3. This is very easy. If we wrongly evaluate it from right, we get the wrong result. So the laptop, in this case, instruct our grammars